Welcome. This will be the second lecture of the 7th week. So, here is a picture that summarizes what we did in the last module. So, our standard scenario is that the wave comes from the extreme left and hits the boundary at x equal to 0. So, there is change of media. A part of the wave gets transmitted into the second medium and another part gets reflected back into the first medium. So, we can identify an incident wave for instance as it is shown in this schematic diagram. So, there is an incident wave which I call y again is the displacement, and this displacement of the particles that constitute the wave would be a function of both space and time. So, y will be a function of x and t. So, there is a transmitted wave which we have designated as y t, and then there is a reflected wave which we have called y r. And importantly, these two media, one that is x less than 0 and x greater than 0, they are characterized by different values of impedances. So, we can write y I as a function of x and t, it is all written here. We went through this in the last module. Okay. So, I will not repeat everything once again. So, all this constitutes the basic setting for the problem. So, the important physics actually comes in what happens at the boundary. So, at the boundary we said that there has to be a matching of the displacements. In other words, the displacements to the left side and to the right side of the boundary at x equal to 0 should be precisely matched. In other words, the displacements must be continuous. Again, you can see why it has to be so, simply because purely from very physical considerations, you can imagine that you can't have very large displacement on one side and just a little bit on the other side you can't have very small displacement. That is untenable. Such a thing cannot happen purely from physical considerations, unless you have some external forces acting on it to do such things. So, we do not have any such possibilities in this problem. So, the displacements will have to be continuous across the boundary. The second condition is that the transverse force, the force that acts in the vertical direction, the transverse force has to be continuous, because if there is a discontinuity in the force, there will be a net force in some direction and it will just carry the whole string in that direction. So, again that does not happen in practice without any external force being applied and so on. In the previous module, we were able to show that the reflection coefficient and the transmission coefficient are simply functions of Z1 and Z2. So, pictorially what we have is that there is an incoming wave, as you can see, which is this. It comes and hits the boundary here at x equal to 0, and what I have tried to show here is when part of the wave has already been reflected off the boundary, and here I have assumed that Z2 is infinity, which means that the second medium offers infinite resistance to the passage of wave, which means the wave cannot actually penetrate through the second medium. So, it will have to be reflected back into the first medium, which is what sort of happens in this case. Let us look at reflection and transmission in terms of the energies, because these waves also carry energy. So, when a wave comes and hits the boundary, it is depositing some energy at the boundary. So, part of that energy is getting transmitted into the second boundary and part of that energy is being reflected back as well. So, today let us go over the same sort of phenomena, transmission and reflection of waves at a boundary, but in terms of energies. I am going to start by recalling our basic formula for the energy of a single simple harmonic oscillator. So, here m is mass of the particle, omega is the angular frequency, a is the amplitude. So, this is the formula for energy valid for a single simple harmonic oscillator. Now, I am looking at the case of a string that is oscillating. So, if I think about this small segment of that string, all that this small segment is doing is to simply oscillate up and down, which means that it is essentially just doing the work of a single simple harmonic oscillator. This also implies that I can simply use this energy formula of a simple harmonic oscillator straight away. Not only that this is oscillating, but the disturbance is actually propagating through the string. That will be equal to half. Now, m has to be replaced by rho, linear density. So, if I am considering let us say a unit, a small segment of unit length, rho would simply be the mass. So, I am replacing m by rho here, omega square into a square multiplied by the phase velocity, which I will write it as c. So, this gives me a formula for rate of transfer of energy along the string. So, this is going to be my basic formula that I will use to discuss how much of energy is transferred along the string. So, remember that this is for a wave that is propagating along the string. So, the first question that I would like to know is how much of energy is let us say coming to the point x equal to 0, which is the interface between medium 1 and medium 2. So, this quantity, the rate at which energy arrives would be equal to half rho 1 c 1, which is the phase velocity of the incoming wave in the first medium, multiplied by a 1 square, that is the amplitude of the incoming wave, multiplied by omega square. Now, the energy that is coming to x equal to 0 is being split between two parts. One is part of that energy is sent into the transmitted wave, and part of that energy is put back in the reflected wave. So, this total energy has to be now distributed among these two components. So, then I should be able to calculate the rate at which energy leaves the boundary, and following the formula that we had written down earlier, that would be half rho 1 c 1 a 2 square omega square plus, of course, this part was for the reflected component. Now, I will write the energy for the transmitted component. So, that would be half rho 2 c 2 b square omega square. The next thing I want to do is to replace this a 2 and b in terms of a 1, and we can do that because we already have this relation that connects a 2 and a 1 and b and a 1. So, from here a 2 will be z 1 minus z 2 by z 1 plus z 2 into a 1. So, I am going to use these relations now. A 2 and b 1 have been replaced in favor of a 1. So, let us simplify this. This is going to give me half omega square a 1 square, that is common, which I can take out, and I will be left with z 1 into z 1 minus z 2 whole square plus z 2 into 4 z 1 square whole divided by z 1 plus z 2 whole square. So, if I take out z 1 again, so I should have half omega square a 1 square z 1, and this is going to give me z 1 square plus z 2 square minus 2 z 1 z 2 plus 4 z 1 z 2 and whole thing divided by z 1 plus z 2 whole square. Now, if you look at the numerator, this is simply z 1 square plus z 2 square plus 2 Z1 Z2, because this last two terms would partially cancel. So, and that is simply Z1 plus Z2 whole square. So, the numerator and denominator is going to cancel out. So, it is going to finally give me just this quantity, half omega square A1 square times Z1. So, this is the energy that's expended in the transmitted and the reflected wave. Now, if you compare this final relation with what we obtain here for the rate at which the energy arrives at x equal to 0 at the boundary, you will see that they are exactly equal. That should not be surprising, because the rate at which the energy is arriving at x equal to 0 is the rate at which the energy is being pumped into the transmitted and the reflected waves. So, clearly there is energy balance, because we have assumed that there is no dissipation. Now, we are ready to write everything in terms of energies. So, for example, so the reflected energy would be, and we already know this quantity A2 by A1 from here. So, clearly that is Z1 minus Z2 divided by Z1 plus Z2 whole square. So, that is the fraction of energy that is reflected back. Now, what about the transmitted energy? So, now let us write a simpler expression for the fraction of transmitted energy. So, clearly now I have these two quantities, which are ratios of reflected energy to incident energy and transmitted energy to incident energy. So, with this we can make a few simple checks. So, for instance, what happens if Z1 is equal to Z2? So, in that case, this ratio, the reflected energy by incident energy, would go to 0, because you have the term Z1 minus Z2. If both are equal, that is going to be 0. And what will happen to transmitted energy if Z1 and Z2 are equal? So, in that case, this term would be 1, because on the denominator we will have 2, let us say Z1 whole square, and that will cancel with 4 Z1 whole square in the numerator. So, if Z1 is equal to Z2, we will get that fraction of reflected energy would be 0, and the fraction of transmitted energy would be 1. That should not be surprising, because after all Z1 equal to Z2 implies that both the media, the one on the left side and one on the right side across the boundary, have exactly the same impedance, which means that as far as the wave is concerned, it does not see a change in media at all if the impedances are exactly equal. Until now we were calculating the energy of a wave that is propagating. So, it is the energy for a propagating wave. Now, what about energy of a standing wave? Broadly speaking, in such a scenario, the total energy is simply the sum of kinetic and the potential energies. So, let us say that I have this string and I am looking at some small segment whose length is dx. So, in such a case, the kinetic energy would be mass times velocity square. So, that is half. Mass here is the linear density multiplied by dx times velocity square, which is this, the particle velocity. Now, I want to calculate the energy over a larger length, in which case I could write E kinetic energy to be. So, this is my expression for kinetic energy. So, the potential energy, let us say in some deformed position, would be simply equal to the amount of work done to deform the string to bring it to that position. So, the work is done by the tension in the string. So, if I have uniform tension T in the string and let us say that a small segment dx gets deformed and length becomes ds. Now, under this transformation, how much of energy is stored as potential energy? So, here I have my expression for the potential energy, which is the uniform tension T multiplied by this deformation, which is ds minus dx. So, if you remember some modules back, maybe a week or two earlier, we wrote down an expression for ds. So, I even gave a short derivation for this segment of length ds in terms of dx. So, this is again under the assumption that it is all within the ambit of small oscillations. So, now that we have this expression for ds, we just need to plug in this expression here, and if you do that, this is what I get. E potential energy is an integral over ds minus dx. ds can be written in terms of dx like I have done here. So, everything fits into this equation. So, I can simplify this further within again the ambit of small oscillations when I say that dou I by dou x is small enough, in which case the quantity inside this red brackets would become the following. Plus there are higher order terms which we shall ignore, because dy by dx is small enough. So, if I substitute this within these red brackets, this 1 and minus 1 would cancel. So, my final expression for the potential energy would turn out to be the following. So, all I need to do is to simply assume a solution for y of x of t, and I need to compute dou I by dou x and y dot. Substitute them here, do the integral and get the answer. So, let me start by assuming that the nth normal mode, the displacement, which is a function of x and t, is given by the following expression. So, in this expression, n denotes the index for the normal mode that we are considering. A n and b n are the amplitudes of the two superposed components, and omega n is the normal mode frequency. Now, to compute the kinetic and potential energy, I need y dot and dou I by dou x. So, y dot would be y n of x comma t, that would be. So, I have computed y dot of x comma t. So, similarly, I also need an expression for dou I by dou x. Okay. So, with these two expressions, now rest of the work is simply substitute it in our kinetic and potential energy expressions. So, let us first calculate the kinetic energy by substituting y dot in this. So, E kinetic is, so I have this what looks like a longish expression for the kinetic energy. Similarly, I will have another one for potential energy. So, remember that these are all for the nth normal mode. So, now we have these two expressions. These are simple integrals to do. So, I urge you to do it, plug in the answer, you should be able to finally get this expression. So, let me indicate by E n the total energy. So, that is the energy in the nth normal mode. So, that will be the sum of kinetic and potential energies. Of course, rho into the total length is simply the total mass of the string. So, that will be 1 by 4 into m omega n square into a n square plus b n square, and each of these integral will contribute a value of half. So, here then we have an expression for the energy of nth normal mode. So, I will close this module with this result for the total energy, and in the next module we will look at what is called an impedance matching condition.